The present work follows the modern approach of combining numerical and analytical methods to analyze the complex dynamics of applied systems. This approach was the basis of the cooperation program between the Department of Applied Cybernetics at Saint Petersburg University and the Faculty of Information Technology at the University of Jyväskylä. This collaboration has yielded a significant output, with 14 PhD dissertations over a 14-year period at the University of Jyväskylä. Some of these defenses received coverage in Finnish magazines. As a recognition to their contribution, Professors Gennady Leonov and Nikolay Kuznetsov were elected as foreign members of the Finnish Academy of Science and Letters. Additionally, 3 dissertations were defended at Saint Petersburg University, where the unique experience of this cooperation program with the University of Jyväskylä was used in 2013 to regain the right to award its own PhD degree. Then, the Finnish-Russian collaboration was continued with the Lappeenranta-Lahti University of Technology under supervision of Professors Leonid Chechurin, Nikolay Kuznetsov and Pekka Neittaanmäki, and support of TFK program grant. And this collaboration resulted in 2 dissertations, the present work and the work of Tatiana Alexeyeva.
I can show you the audience here. That's not empty. I put it like this, in spite of that is Saturday. So these are Victor, Yelizaveta, Anna, and Pekka. And maybe some other people from the street will come, so let's wait.
Recording in progress.
On this occasion, the dissertation entitled Analytical-Numerical Methods for Nonlinear Analysis and Synthesis of Phase-Log Loops by Mikhail Lobachev, Master of Science, will be examined publicly for the degree of Doctor of Science and Technology. I would like to introduce opponent, Professor Vladimir Răsvan from University of Craiova, and yes, yes, and I would like also to declare with this the process of defense officially open. I would like, yes, it's recorded on, and I would like now to give a floor to the candidate to present the dissertation. Please, you have about 20 minutes.
Honored Custos, honored opponent, honored listeners. Let me present my dissertation, Analytical-Numerical Methods for Nonlinear Analysis and Synthesis of Phase-Logged Loops, under supervision of Professor Leonid Chechurin, Professor Pekka Neittaanmäki, and Professor Nikolay Kuznetsov. First, I will shortly talk about synchronization principle and introduce a mathematical model of a phase-logged loop, which is PLL. Then, main definitions of PLL stability ranges, which are hold-in range, pull-in range, and lock-in range, will be introduced in order to outline research questions. Then, I will shortly present methods for nonlinear analysis, which further will be used in order to give answers to the research questions. Finally, the results will be summarized and discussed in connection with further work. In 1657, Christian Huygens invented pendulum clock, and he was trying further to use them to solve a problem of longitude determination on the seas. For accurate determination, stable work of clocks was needed. However, it was stable only when it was a calm. The plan was to attach clock to some heavy mass on the ship in order it wouldn't depend on the rolling seas. Also, Christian Huygens, for more reliability, used 2 clocks and occasionally discovered a principle of synchronization. Consider two pendulums connected by a platform. If we hit one of the pendulums, it starts oscillating, and a bit later the second pendulum starts oscillating too, and after some time they are being synchronized in antiphase. It's an example of mutual synchronization. In parallel systems, so-called master-slave synchronization is used when the phase and frequency of the loop needs to be synchronized to the phase and frequency of the input signal or the reference signal by generating a control signal Vf of t. If the signals are synchronized, then the control signal is constant. However, if the parallel model is constructed in a wrong way, then the signals may never synchronize. So a correct choice of model parameters is an important step in parallel design. In the present work, we consider baseband model of analog parallel, where the phases of signals are considered instead of their forms. Baseband models are widely used in engineering literature, and the corresponding systems of ordinary differential equations can be obtained from classical models by application of special averaging methods. Here x of t is a filter state, theta e of t is a phase arrow, a, b, c, and d define a loop filter transfer function, k VCO is a VCO gain, omega f3 is a frequency arrow, which is the difference between the reference frequency, which is supposed to be constant, and the VCO free running frequency. Finally, VE is called phase detector characteristic, and it is a nonlinear periodic function which makes parallel model also nonlinear and theta e periodic. Since the system is invariant with respect with the following transformation, it can be studied for positive values of frequency arrows only, and further the definitions of stability ranges will be given in terms of frequency deviation. So a Holden range is the largest interval of frequency deviations, such that an asymptotically stable locked state exists and varies continuously, while frequency arrow varies continuously within the interval. And a Pullen range is the largest interval from the Holden range, such that a locked state is acquired for an arbitrary initial state. Roughly speaking, Holden range corresponds to local stability of parallel system, and Pullen range corresponds to global stability. The third interval, Loken range, corresponds to fast synchronization, and the formal definition is the largest interval from the Pullen range, such that the parallel, after any change of frequency arrow within the interval, re-establishes an asymptotically stable locked state without cycle slipping. Notice that the definitions imply that we have three nested intervals. The research questions of my dissertation are devoted to eigenconjecture and problem and to the Gardner problem. It's known that for second order type 2 parallel, the Holden range and the Pullen range are both infinite, and the eigenconjecture is that the higher order type 2 parallels with infinite Holden range also has infinite Pullen range. The Gardner problem is devoted to definition and calculation of the Loken range and Loken frequency. In my dissertation, a numerical counterexample is provided to the eigenconjecture, and analytical conditions for infiniteness of the Pullen range of second, third, and fourth order type 2 parallels is provided. For second order type 2 parallel model with piecewise linear characteristic and with discontinuous sawtooth characteristic, exact solution to the Gardner problem is given. The structure of the work is as follows. 3 research questions are covered by 9 publications, where analytical results, numerical simulation, and combination of both are used in order to obtain the results. Now let me speak about methods for nonlinear analysis. Since parallel models have infinite number of equilibrium points, classical Barbashin-Krasovsky theorem, along with Lyapunov function in form quadratic path plus integral of nonlinearity, cannot be directly used in order to prove global stability of the system, because in this case the condition of radial unboundedness is not satisfied. For parallel systems, it is suggested to use the Leonov theorem, which is the modification of Barbashin-Krasovsky-LaSalle principle for systems with cylindrical phase space. The main differences here is that the Lyapunov function needs to be 2 pi periodic with respect to theta e, and that radial unboundedness condition needs to be satisfied with respect to non-periodic variables. For determination of the lock-in range, let me consider phase portraits of second order type 2 parallel first. So initially, let's suppose that frequency error is negative and corresponding trajectories are in black on the phase portraits, and the system's state is asymptotically stable equilibrium point. Then an abrupt change of frequency error occurs, and our trajectory tends to a new equilibrium point of a new system with positive frequency error. The corresponding trajectories are in red. In the left figure, the re-establishment of locked state occurred without cycle slipping, and in the right figure, cycle slipping occurs because the maximum difference between phase error is greater than 2 pi. For this particular model, the lock-in range is defined by such change of frequency error that our trajectory tends to an unstable equilibrium point by omega separatrice, because for this model, omega separatrices define positive invariant sets which contain only one asymptotically stable equilibrium point. For higher order models, such positive invariant sets can be constructed by using Lyapunov functions level sets. And it's was to notice that for the Lyapunov function we can use the same Lyapunov function which is supposed to be used on the previous step while proving global stability using Leonov theorem. Now let me speak about the results of my dissertation. For solution for the eigen problem, let's consider the loop filter transfer function in the following form, and depending on parameters tau p1 and tau p2 being positive or 0, the resulting parallel model is either second order, third order, or fourth order. Using the Leonov theorem and corresponding Lyapunov functions, the following conditions for pooling range infiniteness of second order model, third order model, and fourth order model were obtained for sinusoidal first detector characteristic. For second order type 2 PLL, the theorem 1 yields that this PLL has infinite pooling range. So that is, the eigenconjecture is valid. In order to construct a counterexample to the eigenconjecture, let's consider a third order PLL with the following transfer function. Using the Raus-Hurwitz criterion, we can obtain this condition for Holden range infiniteness, and notice that this condition is less restrictive than the condition followed from theorem 1, what is in agreement with the definitions of Holden and pooling ranges. In the figure, phase portrait of third order type 2 PLL is depicted, where the parameters was chosen from the gap between these two conditions. This model has infinite Holden range, and two red dots here are unstable equilibrium points. The green dot is asymptotically stable equilibrium point, which magenta trajectory tends to. However, we also can see on the phase portrait this blue trajectory, which tends to this periodic stable oscillation, and this yields that the system is not globally stable, and it is a numerical counterexample to the eigenconjecture. For the answer to the second research question, let's consider second order PLL with piecewise linear phase detector characteristic, which is presented on this picture, on this figure. Piecewise linear characteristic makes PLL model piecewise linear also, and this model can be analytically integrated on linear segments, which allows us to obtain exact formulas for the locking range and solution for the Gardner problem presented in theorem 2. The exact results of theorem 2 were further used to obtain analytical lower and upper locking range estimates for second order PLL with sinusoidal phase detector characteristic, and these estimates are presented on the right figure. The black line here is simulation of the locking range with sinusoidal characteristic. This result was further compared with engineering estimates. In the left figure, we can see that an approximate Gardner estimate intersects both lower and upper estimates of the locking range, and therefore can lead to cycle slipping. In the right figure, the Gardner-Viterbi empirical estimate is between those two estimates. However, it intersects the numerical simulation and also can lead to cycle slipping. For the answer to the third research question, we consider sawtooth phase detector characteristic, which is the limit case of piecewise linear characteristic and which is a discontinuous function. The resulting model is also discontinuous, and rigorous mathematical approach was applied for analysis of this discontinuous system, and it was possible to obtain exact formula for the locking range in this case also. For definition of solutions of discontinuous system, the Filippov approach was applied, where the solutions are defined as absolutely continuous vector functions satisfying differential inclusion. It's interesting to note that the solution at the points of the sliding bands, which are blue intervals on this phase portrait, are not unique. For example, from the point P2, we can emit trajectory either to the half plane theta e less than pi, to half plane theta e greater than pi, and to continue it as a sliding mode solution. Also, it should be noticed that the Leonov theorem allows, in this case, to use only one continuous Lyapunov function, which allows to prove global stability despite of non-uniqueness of trajectories. On this slide, the comparison of locking frequencies of second order PLL models with sawtooth phase detector characteristic and triangular characteristic is provided. It is shown that for the same loop filter parameters, sawtooth characteristic provides wider locking range. To sum up, while the eigenconjecture is valid for the second order loops, the third order loop provided a counterexample to the eigenconjecture. Sufficient conditions guaranteeing an infinite pooling range provided a solution to the eigen problem. For second order type 2 PLLs with piecewise linear characteristic and with discontinuous sawtooth characteristic, and exact solutions for Gardner problem were obtained. These results were further used to obtain analytical estimates of locking range of system with sinusoidal phase detector characteristic, and by application of method of two-dimensional comparison systems. Further, I plan to continue my work on nonlinear analysis of phase-locked loops, and the next step can be estimation of the locking range for second order type 1 PLL with lead lock loop filter, and extension of these results to higher order models by application non-local reduction principle. In this slide, 9 publication which my dissertation is based on is presented. The list contains 3 journal publications, 5 conference papers, all indexed in Scopus, and 1 Springer book chapter. 2 of 3 journal publications are from the first quartile. That's all for my presentation, and now I call upon the opponent to criticize and comment on my doctoral dissertation.
Honored opponent, Professor Răsvan, now you have 15 minutes to make your speech. Sorry for making you waiting for a long time, but now it's right time to...
No, I must apologize. I didn't. I was relying on my previous remembrance, but this happened, I think, maybe already 10 years ago. So I apologize. Now, the problem, in my opinion, just appreciating this extremely interesting thesis. We have in the problem of phase law groups two aspects. The technological one, that means its physical implementation, and the mathematical results and their implications. Concerning the physical aspects, I would like to recall what we already preliminary discussed, that when my master, late Professor Halanai, met Rudolf Kalman at a symposium in Yerevan on technical cybernetics, Kalman pointed, as an engineer, he pointed out the following. He said to Professor Halanai, technology took other ways than those we were prescribing to it. That is why I am thinking all the time at the case of digital phase law groups, while I must confess it's I don't know anything, and it appears to me that still the analog devices are used for the phase law groups. Second, I am really interested in the well-structuring of the phase law groups models that I met in not only in Mikhail's dissertation, but in the previous times when the Lobachev brothers presented other results, other structures concerning the phase law groups, and I must confess that all of them represented more or less something new to me from the technological structure, if you want, and their, let's say, their implementation in a mathematical model. And now I am going to the mathematical model, and maybe when speaking this, there will appear also some of my questions to the honorable doctorand. To have a useful discussion to make me understand some connections that I think to make, but maybe I could be wrong. The idea is the following. If you look at models, they are a feedback loop where you can separate a linear and a non-linear part. The nonlinear part is a periodic function, and you make me to remember our common result with late Gennady Leonov and Professor Halanai. We have a publication on synchronous machines. Gennady Leonov had results concerning synchronizations, all the results obtained in former Soviet Union, in publications that some of them I knew, some of them were impossible to find. And Here I must point out the following. The methods dealing with periodic functions, periodic nonlinear functions, are very close to the method of the absolute stability problems, but not identical. Nevertheless, I must point something in this with respect to this concerning the linear part. When you have the equivalent structure, the linear part will have a double pole in origin. And this is a very tricky and very complicated critical case. That's why I would be interested in telling me, for instance, how did you solve this, how did you, with your methods concerning these double poles. Another remark that I would like to make, and it contains also a question, because I must confess, I don't know the answer. Maybe there are some progress, there is some progress in the field, and I will know from it. It concerns what you cite, the method of the describing function, or as you call it in Russian, the method of the harmonic balance is almost the same. No? It was considered long ago, for many times, that this method covers a contradiction, because in fact you assume existence of periodic harmonic solution, and you obtain necessary conditions. And it was some kind of consensus that this method is not very well established from mathematical point of view. I know only the reference. I wasn't able to get the book of Yefim Natanovich Rosenwasser concerning the harmonic balance and what would you say, the method of integral equations. This was the name of his book, but I wasn't able to get this book to see what is there. So my statement as an opponent is that this method, from what I know, is more or less dubious from the rigor of mathematics. But the question is, maybe you know some progress concerning this aspect. I will be very happy to know that some progress exists. And to continue, another still two aspects concerning the mathematical point of view. The one of them is Barbashin-Krasovsky-Lassalle invariance principle, which we know very well that it works for Lyapunov functions or functional, which are weak from the point of view of Nikolay Gurievich Chetaev. That means that the derivative function does not meet the initial conditions of Lyapunov, and so you need to study the omega limit sets and so on. But it's very suitable, at least in the papers of Lassalle. Barbashin and Krasovsky, they dealt only with the equilibrium as the origin. The results of Lassalle are very suited to systems with several equilibria. But the results were communicated by Leonov and his co-workers at the time meant the following, that you have some global behavior of the systems with several equilibria, but this doesn't mean that within your omega limit set, where you have only equilibria, there are not unstable equilibria there. And probably I am putting the question, isn't here hidden some truth concerning this, how you say, the range of the frequency and so on, because you have to avoid unstable equilibria, and why not unstable generating hidden oscillations, if you like. because the global behavior of systems with some equilibria doesn't tell you which are the not unstable equilibria. And the last question I would like to point out is a question concerning your application about, let's say, discontinuous functions and the methods concerned arising from Filippov and dealing with these problems. Is this concerned with sawtooth nonlinearity? Because this nonlinearity is not discontinuous, is not smooth, its derivative is discontinuous. Maybe somehow this derivative is again hidden in the model. I don't know. So you can consider this a question. I didn't look at my watch. I don't know. Is the quarter of an hour is less or more? I apologize in any case. But the discussion is extremely interesting. You do things that are far going. This is my opinion. So I end it for the time being.
Thank you, honored opponent. I think we naturally slipped into the question and answer session. So please, Mikhail, could you please address, at least I counted 3 very interesting questions from honored opponent. Please, Mikhail, dear honored candidate, the floor is yours.
Yeah, honored opponent, I remember at least 5 questions. So let's start, for example, from describing function method or harmonic balance method. Indeed, it is not mathematically rigorous method, and it's interesting to notice that in this dissertation, in my work, in the very first publication, despite it's not a rigorous method, the results were obtained after an attempt to apply this method for analysis of oscillations in PLL. There is indeed an attempt to make this method more mathematical, and it was done by Gennady Alexeyevich Leonov, and he formulated some theorems, and it is what is called problem method of small parameter and method of continuation by the parameter. And the idea here is that, for example, we know, I guess, some linear system which have oscillation, and it's written in the form the right hand side having this linear system plus epsilon multiplied by nonlinearity, and then having oscillations in linear system, we slowly increase this epsilon parameter and trying to localize these oscillations in nonlinear system also. And this is what's called the method of small parameter by Gennady Alexeyevich Leonov. And as I know, this approach also led to discovering of hidden oscillation concept. So for this particular system, third order system PLL, the harmonic balance method and the method of small parameter, in some sense, it didn't give a result, because the solution, periodic solution, which was found by this method, was classified as unstable solution. And in this phase portrait, this unstable periodic solution is depicted by shadow curve. Further, method of stabilization of unstable solutions, Pyragas method, was applied to the system, and it was shown that this Pyragas method provides that this black curve is unstable periodic solution by the Pyragas method. So that's my comments about the harmonic balance method, and I think that I can continue about other questions. So maybe let's discuss the question of weak Lyapunov, of usage of weak Lyapunov functions. In the original work of Barbashin and Krasovsky, it was formulated, two theorems were formulated. The first one needed to Lyapunov function not weak, but regular Lyapunov function to be found. And in the second theorem, it was said that if on some set, let's say M set, the Lyapunov function is the Lyapunov function derivative is 0, but if this set doesn't contain any complete orbits, that this Lyapunov function can be used in order to prove what it was called stability in large, I guess, in their terminology. Understanding that we have one asymptotically stable origin and all solutions tend to this origin. So for Leonov theorem and its usage for systems having two zero poles at the origin of linear model, it's important to apply this weak Lyapunov function, because talking about the question of zero pole in loop filter, it's and about the question how to apply frequency methods for analysis of these systems where we have in some sense limit or critical case. It is possible to use a change of variables, and if in new variables we can have the system without this frequency arrow. So the first loop filter state, the first component of the loop filter state can deal with frequency arrow, and for the other n-1 dimensional part of loop filter, we can use Lyapunov function in form in the quadratic part form and use the frequency theorem. And that is how for this particular system the results can be extended, I guess. And while calculating the derivative of the Lyapunov function, we have know the first component of the loop filter state, so we cannot use in this sense weak, not weak Lyapunov function. So it's indeed important improvement for the theory to use weak Lyapunov functions. And probably about your question about sawtooth characteristic. In my work, the sawtooth characteristic is defined like in this figure, and in this figure the characteristic has discontinuity points on and at points p pi n. So probably it depends on the definition. The same divergence in terminology we can see reading, for example, engineering and mathematical books, both for PLL. Honored opponent, I could forget some of the questions. Maybe question about applicability of analog models, maybe the last one. My work continues the findings of our research group and the previous dissertations of Marat Yuldashev, Renat Yuldashev, Konstantin Alexandrov, and Mikhail Blagov. In the first two works, averaging methods were applied to classical PLL models in order to obtain and discuss why engineers can use these so-called baseband models, which are autonomous and which are easier to analyze. And also talking about this particular model studied in this dissertation, I can say that for sinusoidal phase detector characteristic, the same model is can be obtained. The same system of differential equations can be obtained by from SRF PLL model, which is three-phase modification of classical PLL, and also the same equations describe two-phase PLL models, which are presented within my publications included in the dissertation, but I didn't put them on this slide. And talking about, for example, SRF PLLs, nowadays there are many of publications devoted both continuous and discrete type equations, for example, of SRF PLLs. And further, the nonlinear analysis and this work also can be continued for analysis of discrete type PLLs and models. So thank you for these comments and for these questions.
Honored opponent, Professor Răsvan, are you satisfied with answers?
Absolutely. It's okay.
Are there any other answers left? Would you like to discuss anything, or we can go to, let's say, conclusion part from your side?
No, I consider that from my point of view, it's everything over.
Honored opponent, so please, the floor is yours. You have to make a summary concluding if you consider a honored candidate to be awardable, his work complete, and the way he defends the finding is of the level of PhD. Please summarize, if possible, shortly. What do you think about?
Well, I would like to appreciate both the structure of the PhD thesis, the way of formulating research questions and answering these research questions and illustrating this by publications, This is extremely important to show the originality, the fact that the research are original and not yet known by the community of the researchers. That this is extremely important to show that this is a research dissertation is more than what is considered now in the European Union and the United States the third cycle of learning. To speak about PhD student, because in our time this was considered a way of forming a high-level researcher and not just a student, and this was valid at least for the engineers. And now I'm seeing a genuine research dissertation with research questions, results, methods of analysis, and publications. We have nine publications of various types in good journals, in good, let's say, anthologies of results, that books of studies. So, from my point of view, this is a high level of a PhD students. If you want, it's more than a PhD student result. It's a result of a good researcher who is integrated in a group of research, but at the same time, he is able to work independent. And from my point of view, it's personal, it's true. That's what is to be appreciated and praised in for a PhD thesis defendants. From my, I think that honorable dissertant will be a perspective and a good researcher, provided he would like to continue this interesting thing. The group will continue to accept him and to stimulate him, giving more interesting results, interesting problems, if you like. From this point of view, I don't know if this is too early to congratulate, but it's a personal impression. I like this thesis, as I used to like what was coming from the group of Gennady Alexeyevich and now of Professor Nikolay Kuznetsov. That's what I want to say. I don't know if it is according to the regulation of the university, but at any case, it's what I am sincerely thinking.
Thank you.
Thank you, honored opponent. And I now call upon anyone who has anything to comment on my dissertation or its defense to ask the Custos for permission to speak.
I think it's the right time to show the audience because it exists. Please. Any questions from audience, please? Maybe super quick, rather not a question, but a request from my side, as I am also part of the audience. When we talk about these transfer functions and nonlinearities, honored candidate, can you give an example of technical realizations, what they stand for? There was only one technical example with a wall watch, and otherwise you speak just about the functions. But we are in technical university, so we have to see through these formulas applications. Could you please just briefly discuss in which electrical systems, circuits it can be applied? Thank you.
Honored Custos, thank you for the question. I would like to, I don't remember the number of the publication. in one of the publication number 4, we provided a electrical scheme for realization of the loop filter, which was used for providing a counterexample to the eigenconjecture. And also this model was realized in MATLAB Simulink. And as I said earlier, another examples of realizations of such models, for example with this loop filter, are synchronous reference frame phase locked loops. Thank you for the question.
Any other questions, comments, statements from internet? Nothing. So then with this, I declare the public examination is now closed. Thank you to everyone. Yeah. Thank you so much, Professor Răsvan, for...
You are welcome. As you say, I was honored to be again with the collective, and I regret of not being able for all of us to meet physically. It's a pity, but it does not depend on us. And I would like to add, because you asked the technical realization of a phase lock loop. Now you have, if you see my words, a phase lock loop is a small integrated circuit who anybody doesn't know what is inside. You can just guess by doing tests. And I can remember from my electronics souvenirs that at the beginning, when I was an engineering student, you have electronic lamps, transistors with just a characteristic in the catalog. When we started to have the circuits of analog devices from United States, you get what was called an application note for a small circuit, and this application note was a small book telling you tests, what utilities, but you still couldn't know what is inside. So concerning realization physics, who knows what technology will give to us.
Thank you. Of course, I expected circuitry answer, yeah, but I wanted, to make it more transparent for public and for the record that these are not,
I see, of course,
not just differential equations, but there is some technical system behind of it, and it is very important because we are in a technical university, so we want just to be, how to say?
Well, I graduated in the technical university, but at that time was called, as you maybe remember, Polytechnic, that is Technical Institute, this one, and now is the term university for the ranking, but Polytechnic is something different.
Okay. Professor Răsvan, what we will need from you by Monday is a formal statement.
You can be sure that I have it, because for the case of Mikhail, I acted firstly as the examiner.
Yeah, right.
So this, what I was telling there is to migrate what I was telling there for him. Concerning the next PhD, I will be ready in time up to Monday, because on Monday I'm leaving for Italy, but we have still enough time to do the statement. What I am genuinely regretting is that the highest mark that I have to propose is should be based on comparing with other theses. And I don't have enough information for give that 10-15% of the thesis.
Pekka wants to say something. Yeah.
Maybe we will discuss V3 only now.
Yeah.
We close
Yes.
discussion because it is, and then we continue.
Only among us, yeah?
Yeah, yes.
Okay.
No, four, sorry.
4 of us, okay.
4.